For this example, we want to start with the function f of x equals the absolute value of x. And then in parts A and B, we've transformed this function. So we want to identify what transformations have been made, and then sketch a graph of this function. And then based on the graph, we can identify the absolute max and minimum values of that function. So in part A, we have g of x equals the absolute value of x plus 5. So to identify what changes, what transformations have been made, here we have a plus 5 on the outside. So since this changes on the outside of the absolute value, outside transformations are vertical transformations. And since we're adding the 5, this is a vertical shift up 5 units. So what this is going to do, here on the right we have the graph of the absolute value before any transformation has been made. So for example, a point, say, at the origin, which is on the absolute value function, 0, 0, this gets shifted 5 units up to 0, 5. So here's going to be the transformed point. And we do this for every other point on the absolute value. So the point at 1, 1, well, this gets moved up 5 units to 1, 6. And that would wind up over here. And we shift every point up. And in the end, we get a graph for the absolute value, which looks something like this. Okay, so we just take this graph and move it up by 5 units. And so what we can see is right over here at the point 0, 5, there is a local and absolute minimum. And since the graph continues to go off to positive infinity in both directions, we have no absolute maximum, or for that matter, local maximum. Okay, and so what we see is that as x goes from minus infinity to 0, the function is decreasing, and as x goes from 0 to positive infinity, the graph is increasing. And now on the next slide, let's take a look at the example in part B. Now in part B, we have the following function: g of x is minus the absolute value of x over 3 plus 2. So notice here we have a number of changes. We have 3 of them. 2 of them are on the inside, dividing by 3, adding 2 on the inside, and 1 of them is on the outside. So here we need to not just identify the transformations, but pay attention to the order in which we do them. And so one way to do this, one method that we talked about earlier, was by starting on the inside. And if I first take into account the plus 2 on the inside, this is going to be a horizontal shift in the negative direction to the left by 2 units. Then we can do the next inside change, which is this divide by 3. And so when we divide by 3 on the inside, since it's on the inside, it's still going to be a horizontal transformation. This is going to be a horizontal scaling by a factor of 3. And then lastly, we have this negative sign on the outside, and this is going to be a vertical reflection. And when we reflect things vertically, we do them across the x-axis. So we can apply each of these one by one, and then we can take a look at the end result and then identify where or if we have a max or a minimum of this function. So let's start with the base absolute value function. And we can track where a few of the points go, but every point is going to move 2 units to the left. So for example, the point 0, 0, this is going to get moved 2 units to the left at minus 2, 0. The point at 1, 1, this is going to get moved to the point at minus 1, 1, 2 units to the left. And the point at minus 1, 1, this gets moved to the point at minus 3, 1, 2 units to the left. So plotting these points, here was minus 2, 0, here was minus 1, 1, and here was minus 3, 1. We get the following graph. Okay, and what this again is the result of just taking the graph that we had in black, shifting it 2 units to the left. After we apply this horizontal shift, the next thing we do is a horizontal scaling by a factor of 3. So to check where each of these goes now, we're going to multiply the x-coordinate of each of these points by 3. So this point at minus 2, 0 goes to minus 6, 0. This point at minus 1, 1 goes to minus 3, 1. This point goes to minus 9, 1. Okay, so each x-coordinate gets multiplied by 3, and let's track the result of this now below. So we have a point, the vertex now winds up over here at minus 6, 0, and minus 1, 1 goes to minus 3, 1, so that is right here. And the point at minus 3, 1 gets moved to minus 9, 1 over here. And connecting the line between these points, we get the absolute value, which has been horizontally stretched. So we've taken the graph above in red, and we've stretched it 3 times further away from the y-axis to get the graph in blue. And now the last thing that we do is we take each of these points and reflect them vertically over the x-axis. So this point at minus 6, 0, it stays on the x-axis at minus 6, 0. The point at minus 3, 1, this now winds up at minus 3, minus 1. And the point at minus 9, 1, this winds up at minus 9, minus 1. So we flip each point over the x-axis. That changes the sign of the y-coordinate of the point. And that means down here we can mark these points and then connect them with a graph. So here we are at minus 6, 0. The point at minus 3, 1 gets reflected to minus 3, minus 1, and the point at minus 9, 1 gets reflected to minus 9, minus 1. And so here is our graph in green. Okay, and so now this graph is going to continue down forever. So that means we're not going to have a local or absolute minimum. But we do have a maximum right here at minus 6, 0. So we have absolute and local maximum at this point at minus 6, 0. So the function is increasing from negative infinity out to minus 6 to x equals minus 6, and then from x equals minus 6 out to positive infinity, the graph is decreasing.